Plate tectonic theory was not accepted for centuries because no one could adequately answer the question, what is the mechanism that drives the plates? In the late 16th century, Abraham Ortelius, in compiling New World Explorer maps, noted that by carefully considering the coastlines of the Atlantic Ocean, it appeared that the Americas had been torn away from Europe and Africa by, he theorized, earthquakes and floods. Over the next 3 centuries, other proponents of an original single continent included Francois Paget, who invoked the sinking of the land between the continents to create the Atlantic Ocean, Georges-Louis Leclerc, who resurrected Ortelius's theory of a great earthquake and floods pushing the land apart, and finally Antonio Snider Pellegrini, who proposed that the shape of the continents, supported by fossil evidence, argued for the origin of a single continent, which not only joined the continents across the Atlantic Ocean, but also included Australia. No one, however, could explain how the continents moved. Bathymetric surveys in the following decades unveiled an extensive submarine mountain ridge between the continents that ran the length of the Atlantic Ocean. Meanwhile, seismic data began to reveal Earth's layers, a core, a crust mantle boundary, and a thick outer layer called the lithosphere that lay above a less dense asthenosphere. In 1912, German meteorologist Alfred Wegener, also intrigued by the fit of the edges of the continents, championed the concept of continental drift, based on his study of similar rock types, geological structures, and fossils on both sides of the Atlantic. To make it work, he hypothesized that the mechanisms causing the drift might be the centrifugal force of the Earth's rotation or the change in its axis of rotation. Wegener also speculated that, quote, the mid-Atlantic ridge is continuously tearing open and making space for fresh, relatively fluid and hot material from depth, end quote. His views were considered preposterous and improbable, and were rejected by most Earth scientists. Following the discovery of radioactivity in 1896, it became clear that Earth's interior was heated by radioactive decay, and that the insides would be largely molten. Indeed, by 1926, a liquid core was determined. In 1927, geologist Arthur Holmes, studying radioactive decay, proclaimed that mantle convection was the answer to Wegener's missing power source to drive continental drift. He based it on the fact that as a substance is heated, its density decreases, and it rises to the surface until it cools, when it sinks again. But convection of the solid mantle alone was still unpalatable to most geoscientists. Nuclear bomb testing in the 1950s motivated the establishment of the worldwide standardized seismograph network to monitor explosions, prompting a greater concentration of seismograph stations. The increased data allowed seismologists to precisely locate far more earthquakes, revealing that most occur in discrete areas, near trenches and along mid-ocean ridges. Decades after Wegener's death, geologist Marie Tharp, left in the lab to examine data from ocean floor field surveys, theorized that mid-ocean ridges appeared to be extensional rift valleys formed by plate motion, thus paving the way for the acceptance of Wegener's continental drift theory. Her colleague, Bruce Heezen, initially skeptical, published her work in 1956 under his name, but ascribed the extension to an expanding Earth theory. It wouldn't be until the mid-60s that he would accept Tharp's interpretation of plate motion. Curiously, it was Harry Hess who, in 1962, was credited for recognizing that oceans did grow from spreading ridges. He also defined ocean trenches as locations where ocean floor was destroyed and recycled, but he too lacked geophysical evidence to confirm this theory. Just 1 year later, this concept was supported by ocean floor magnetic surveys that revealed symmetrical patterns of magnetic striping on either side of the mid-ocean ridges. These stripes were found to be the same age at similar distances away from the ridge on each side. While pondering the mystery of how volcanoes, such as the Hawaiian island chain, could be so far from spreading ridges or subduction zones, Tuzo Wilson proposed the plates moved over hotspots. Following this breakthrough, with the discovery that ocean ridges were connected with transform faults. The science rapidly blossomed with the definition of the 3 main plate boundary types: divergent margins, where plates move apart; convergent margins, where plates push together at subduction zones or mountain ranges; and transform margins, where plates move horizontally past each other. As geophysical evidence supporting plate tectonics accumulated during the 1960s, scientists revived Holmes' theory of mantle convection as a driving force for moving the plates. Mantle convection assuredly plays a role, but it doesn't explain how some plates creep along faster than the convection currents beneath them. This led scientists to a fundamental force: gravity. Gravity acts on the tectonic plates, resulting in what are now referred to as ridge push at the spreading ridges and slab pull beneath subduction zones. This is an evolving science that not only involves these three forces, but involves friction and much more, leaving scientists to ponder: what will be the next tool that helps reveal new facets of plate tectonics?